I am Mohammad Rafiqul Islam, Superintending Engineer, Public Works Department, and the team leader of Working Group 2 from Bangladesh side, and my counterpart is Professor Maeda Masaki of Tokyo University. So today I will discuss about the basic of Seismic Assessment Manual prepared under PWD, and that manual is basically followed from the Japanese standard. And since Japanese standard is not so familiar in Bangladesh, so I'll speak about the basics, and this will help the participant to clearly understand the successive lecture. So before that, I will speak about some background. In the Standing Order on Disaster 2010 version that was signed by Honorable Prime Minister, and there were some guidelines for the PWD, and the major responsibility was some major responsibility was preparation of the seismic evaluation manual for seismic capacity evaluation. So that's why we prepared the manual. And another major objective guideline was for PWD preparation and periodically update the list of the vulnerable structure, and dissemination the technical information or knowledge related to earthquake to general engineer or professional. And seismic assessment manual to preparation was the objective, but in the BNBC there's almost nothing about the seismic assessment of existing building. The BNBC is basically for the design of new building, and that defines to cover the minimum criteria for design of the new building. Since the time, I think allotted time is very short, so I'll go a bit faster. So, and then we started a project, CNCRP, that is basically a capacity development project of PWD engineer, and also preparation of the manual. The major objective of that project that was started in the 2011 with the cooperation of JICA was the capacity development of PWD engineers for seismic assessment and retrofitting of existing building. And also the preparation of manuals, that was the mandate of from the SOD, preparation of the manuals for seismic assessment and retrofitting, and as well as the dissemination of that knowledge to our professionals. And with a view to prepare the assessment manual, we started work with our Japanese colleague, and it was found that the building in Japan is quite different from that building in Bangladesh. So the building is the structural member is very narrow, especially the column size is very narrow, low strength concrete, and also the construction procedure. There are many differences between the building in Japan and Bangladesh, and that's why we did some structural test in 2012 and 13. Total 13 specimen was tested, and the major objective of the test was to understand the behavior of narrow column that is common in Bangladesh. Usually 10-inch column was very common in existing old building. The behavior of narrow column for lateral loading, to take the performance of poorly anchored river at end of the column, that is also very common, and to understand the behavior of RC frame with infill masonry wall, that is also a local characteristics in Bangladesh that is not available in Japan, to check the performance of plain river in old RC building, to check the performance of low strength big aggregate concrete, that is the low strength concrete or high axial loaded column, to know the strength and ductility of existing old RC frame building of Bangladesh, and finally to get required data for preparation of assessment and retrofitting design manual for Bangladesh. And this is the some photograph of 13 specimen that was tested. Here are I think the 7 picture that covers almost the different characteristics of Bangladesh building, that is narrow column, low strength, infill masonry, and the inadequate anchorage of the column, beam river into the column. And this is some backbone curve of that from that experiment. And then finally, we prepared the seismic assessment manual. At the time, we prepared 5 manuals. There are 4 manuals. One is the seismic seismic evaluation manual, then seismic retrofit design manual. And if the seismic retrofit is started, then the construction procedure and the supervision method is guided in this manual. And finally, there was another manual that is the objective of the disaster risk reduction. That's why we prepared a manual for the new building design, considering the draft version of the BNBC prepared until 2015. And there was another manual that is non-seismic hazard manual, non-seismic others. We have wind, tsunami, maybe those manual was also prepared. And now I will discuss about the concept. What is the relation between the Japanese procedure or the PWD manual, but now I'll speak about the PWD manual, specific evaluation manual, and the BNBC.
Mr. Rafiq, please,
sir.
Sorry, you discuss about the non-seismic
non-seismic hazard manual. Sir.
Hazard. That you mean the ILA, SIDOR, other natural disasters?
Yes, sir. Yes, sir. Other than earthquake, yes, sir. Other than seismic, there are many other
natural disasters,
including the tsunami, SARS, many other wind also.
Okay. Major. Okay, thank you.
So, thank you, sir. So, thank you for your queries. According to BNBC 2020, the very recent BNBC, formula of base shear is SA into W. That is, I think, almost now already all of our professionals and academicians are familiar with this formula. So SA is 2/3 of Z into I importance factor and CS divided by R into W. And we, from the FEMA, this is the FEMA graph, that we know that the R, that is structural modification factor, that is covered due to the R. Sometimes for the R there are several values based on the detailing of the detailing or ductility of the structural frame. So R is basically, it comes from the two function. That is, one is the this is the elastic response structure, and this is the design base shear, and R is one is from the overstrength factor omega, and another is the ductility factor from the ductility scum. So we can write R into RD into W omega. So just I am deriving how we can go into the our PWD manual basic consideration. So now we can write V equals to in this way here, and again converting this base shear divided by W, this W into RD into omega, and other thing in the right side. And here the V into omega, this is V as into omega So this is the strength of the structure. Initially, we designed at this level, but finally, maybe with addition, other, there are some redundancy in the structure, as well as we did more rebar than that is needed from the design. That's why we have more strength than from the base shear strength. So this is the strength of the structure, and it is divided by W is the strength index, C. So this strength index is an important term in the seismic evaluation manual. Another important term is the ductility index, F. So RD is the ductility, the from elastic capacity we divide with the another by ductility factor. Mm. So see, this is RD. So RD is similar to Japanese ductility index. So now we can write that this is the strength index and this is the ductility RD and equals to this. So this is the main formula of Japanese or PWD manual. So, and this side, all these are the parameter of BNBC, that is the Bangladesh parameter, that is Z is the zone coefficient, I is the importance factor of the building, CS related to the natural period and the subsoil of the structure. So this is the capacity of the structure. This is the capacity, and this is the demand. Here, all the term relates to the demand of the structure, and this is the capacity. So this is the main formula of the our manual. So which is related to the BNBC. That's I want to mention that part. And this is we call the capacity, and considering the inelastic behavior, the demand is reduced by 80%. And say for example, the demand of at Dhaka for low-rise building will be, if we put the value, it will be around 0.3. So if the building, the capacity, the multiplication of strength and the ductility is more than 0.3, then the building is safe. So this should be judged for a building in each direction and each story. So there are two main unknown factor is the strength index and the ductility index. So now I will just speak about the strength and ductility. I think almost all are familiar with this term, but even though I just speak a little about those. So is the strength is the how we calculate the strength. Strength, there are two consideration of strength. One is from the flexural capacity of the column. So if it is a column, then maximum moment capacity of the column is considered, and then from at this stage the shear is the shear is defined as QMU. So QMU is the M1 plus M2 at both ends and divided by clear height of the column. And there is another capacity of the column, that is from the transverse rebar. So that is defined as the QSU. So which one is smaller is the strength of the column. And usually we calculate this is the strength, Q is the strength, and if it is divided by the load, axial load on the column, it is called the strength index. And this strength index is sometimes modified by the story shear modification when we go to the above story from the ground floor. And another term I told about, the important term is the ductility. So ductility is the capacity of the building material, system or structure to absorb energy by deformation into inelastic range. I think there's almost nothing to say about this. So initially, this is the elastic response of a structural member. So this is the force, and um, this is the deflection. So from the equal energy principle, we can convert this the energy with this energy, convert into that energy, and then uh, uh, we can derive this simple formula. F ductility index is equal to root over 2 mu minus 1. So this can be derived. I think no need to discuss here more about it because of limited time. And for our in the manual, it is calculated from the various deflection angle. That is, so for say for a column, when we judge a column, its maximum deflection R max and yield deflection, shear deflection, various deflection is calculated, and then finally it is calculated from some formula. This is, if we can calculate those, then we can finally calculate this formula. From this formula, the ductility index. And for those, we have to know the column size, clear height of the column, axial force ratio, shear force ratio, tensile reinforcement ratio, many other things we have to know. And then finally, if we put those, we can find the ductility index. This is the way how we calculate the C and how we calculate the F. So after getting those, we can calculate the, sorry, we can calculate this capacity F into C into F, structural capacity. So method of seismic vulnerability is first to calculate the seismic index of the structure. This is the E0. E0 is the basic seismic index of the structure, that is the C into multiplication of C into F. SD, this capacity is later modified by the irregularity index. This is the irregularity index, and this is the time index. Irregularity, if there is any irregularity, it is modified, and this value is usually less than 1, and T is the time index. Due to deterioration of the structure or other reason, it is applied. So this value is also 1 or less. So that's why we calculate the structure final capacity. And if a structure is very ductile, then its all the column is ductile, then its load deflection diagram is like this, and this is its capacity. And if the building is very rigid, then its load deflection curve is like this. Very high strength is high, ductility is less, and its the capacity is like this. And this is two building, one say A and B. One is resist earthquake by strength, and the resist earthquake by ductility. But in a building, there might be two types of columns. Some columns are ductile, and some columns are brittle. So in that case, its capacity will be first the strong column will take the lateral load, and the load deflection curve will be like this. And this is then if the strong column fails or its capacity reduced, then the ductile column will activate more, and it will take the remaining, show the remaining capacity. And that's why we finally, when we calculate the E0, I told about the E0. The E0 is the basic seismic index. So E0 is calculated based on the capacity of various type of vertical member. So there are some member, short column, shear wall, or some ductile column. So one by one its capacity is calculated. So there are actually two way to calculate the E0 basic capacity. One is by the contribution of the strength of the structural member, and another is the considering the ductility of the vertical members. So first one is called the strength dominant basic seismic index E0, and second one is the ductility dominant basic seismic index E0, and its final basic seismic index will be the E0, which one is more. And SD, I said the irregularity index, that's it is used to modify the E0, and also time index, it is also used for modification of the E0. And after getting that SD and T, we finally calculate the IS. And again, another issue is ISO. For ISO, I already shown that ISO is the this value 0.8 into 23, and all these values are the seismic parameter from the BNBC. And after say I already shown that for Dhaka that could be like this based on the medium stiff soil and low rise building. And when we get the both IS and ISO, then judgment is applied by two way. One is it is checked that whether IS is more than ISO, and another is its minimum strength, whether it is more than this value. At CTU is the cumulative strength at ultimate deformation of this. At ultimate stage, it must have a minimum strength. There should be more than this value. So this judgment is applied for each story and each principal horizontal direction of the building. And to prepare this manual, we also did accept the specimen test. We also did some time history analysis to take the behavior. Also did some validation of the existing building with our BNBC. After completing all those, we have also prepared our manuals. And this is one figure of past damage, earthquake damage in Japan. And here in Japan, it is shown that the building, the hatch line are the damaged building. In Japan, it is found that the building which IS value is more than 0.6, that is safe. But if it is less than 0.6, then those building is less, that building suffered damage. So that's why in Japan the judgment point value is 0.6. This is the that is I talked about the assessment. And about the retrofitting. So if this is the capacity, or if this is the capacity graph of existing building, and this is the demand line, so we can enhance its ductility to pass this line, or increase the strength of the existing building, or we can increase both strength and ductility to upgrade the existing building capacity. So this is the way or objective of the retrofitting. In preparation of the BNBC, in preparation of the PWD manual, we have found some problem. Though we studied those problems, we have also addressed in our manual about those problems. That in the problems are the low quality construction, as so this is the low strength concrete, high axial force. This is another problem in our country. Also, the many existing building, the hooks are 90 degree, not at present stage what we follow 135-degree hook. Also, the river is not anchored here. This is very straight and not adequate anchorage. There is also infill masonry, which affect the performance of the frame. The joint is also, beam column joint is also poor, and the splicing is not proper in the beam as well as in the column. And the joint area is very narrow. That type of issue we address in our manual, and we also give providers some guideline. We also provide some guidelines. Say, for example,
Mr. Rafiq, sorry, I
sir.
just want to know, as you discuss hook 90-degree left, but from PWD design side, we, as we know, if
Sir.
deformed bar is provided in the structural member, there is no need to hook or lab, this kind of what we have known from your side, from PWD design side. But from the structure, seismic point of view, I think this hook and lab is mandatory.
Yes, sir. In the actually, according to code, the 90-degree hook or element is a mandatory obligation for the for beam. So, sir, for seismic as well as non-seismic, but there was a common saying in Bangladesh. Even it was well known in the private sector also. So actually, our manual is prepared, sir, not only for the PWD building, for the common in Bangladesh. So this is some common phenomena. In case of when deformed river came in our country, in case of plain river, we usually used 180-degree hook like this. But when the deformed river come, so some of the engineers thought that in case of deformed river, no need of hook. So that is common. That is a problem in case of some of the existing building. That's why we studied this and we found this is a problem. So we address those problems in our manual, PWD manual, and we give some guideline, say some 20% reduction or something in our manual. And finally, we also told this is a tentative suggestion and needs further research and experiment for verification and modification in Bangladesh. Though we tested, but we spoke about more testing, more research about those issues. So that's why the SATREPS-TSUIB program started according to after our recommendation, as I know. So in the SATREPS project, out of this problem, the problem that was addressed is about the low strength concrete and high axial force. Also this anchorage problem. Also the infill masonry was also addressed, and the flat plate structure that is not we address in our PWD manual, that is also addressed. And with those, the SATREPS is now preparing the extended manual of the PWD manual, and that will be, this issue will be I think later the presenter, they will discuss about this issue, what to do about this issue in case of seismic assessment. And PWD also upgrading its present manual. And finally, I will speak about some project of the JICA, so that our participant, those are who are not familiar of this project, so just they will hear about the project name. So for their clear understanding, I will speak about those projects. So this is the basic project. CNCRP, PWD started this project for capacity development. This is a capacity development and also preliminary preparation of the manuals. And after this project, we started another project now going on BSPP, that is functioning from the PWD. That is the project of PWD. This is the knowledge dissemination project. There are many components, but the main objective is the knowledge dissemination, and from that knowledge we gained in this project. And from this project, we refer that I speak about this issue, that we have found some problem and we refer about more research, and that's why the SATREPS-TSUIB project started. Now it is going on as a project of HBRI that started 2017. Now it may be 2022. And there is another project of JICA that is in PWD. That is the implementation project. That
excuse me, okay, sir. How long do you need to finish your presentation?
No, this is the last slide. This is the last slide. Sorry.
Please.
So
Okay, please
okay. Thank you very much. This is my also sorry.
Okay.
Thank you for your passion sharing.